In modern aerospace, the standard approach is to test every component on the ground until perfection is practically guaranteed. SpaceX took a different route. They built the largest rocket in human history, flying full-scale hardware with the explicit expectation that it would fail. During its first integrated flight test, the vehicle successfully cleared the launch tower, but as it climbed into the upper atmosphere, the rocket lost altitude, tumbled out of control, and failed to reach its targeted ascent orbit before the flight termination system was triggered. The sheer thrust of the initial liftoff had immediate consequences on the ground. The force from the Super Heavy booster's engines completely shattered the concrete orbital launch pad, sending debris flying across the test site. To solve this bottleneck, engineers completely overhauled the launch mount. They installed a massive water-cooled flame deflector and poured a heavily reinforced steel and concrete foundation to absorb the intense acoustic and thermal shock. This data proved that the water-cooled steel plate was a viable solution, allowing the launch mount to survive subsequent flights with minimal maintenance. By testing the pad to its limit on Flight 1, SpaceX gathered the information required to stabilize ground operations. This vector blueprint breaks down the mechanical scale of the vehicle. At the bottom is the Super Heavy booster, powered by 33 Raptor engines, and stacked on top is the upper stage ship, driven by a cluster of 6 engines. With this immense scale, a traditional stage separation, where the booster shuts down entirely and releases the upper stage before its engines ignite, takes too long. During Flight 1, that delay bled off critical momentum, causing the vehicle to lose control. The engineering solution was to eliminate a delay entirely by adopting a maneuver known as hot staging. This fluid dynamics visualization shows the upper stage engines igniting while the two vehicles are still mechanically attached. The specialized interstage ring allows the highly pressurized exhaust gas to vent out the sides, meaning the upper stage literally uses its own thrust to push itself away from the booster. Overcoming the stage separation bottleneck allowed the vehicle to maintain its velocity profile perfectly. This hardware adjustment was the specific threshold SpaceX had to cross to reliably push the upper stage out of the atmosphere and into the vacuum of space. Once ascent mechanics were stabilized, the engineering focus immediately shifted to the extreme physics of bringing the hardware back down. The primary objective was to master booster recovery right back at the Boca Chica launch site. That effort produced a significant operational milestone. The launch tower's mechanical arms successfully closed around a descending, hovering Super Heavy booster, catching it in midair and proving the physical viability of rapid reuse. But the testing did not stop at a successful catch. During Flight 9, engineers intentionally pushed Booster 14 to its aerodynamic limits, directing it offshore and commanding a significantly steeper angle of attack during its descent over the Gulf of Mexico. The increased descent forces from that aggressive angle proved too much for the internal plumbing. A propellant line ruptured inside the booster, mixing liquid oxygen and methane and triggering a massive explosion roughly a kilometer above the water. Pushing the booster to its physical breaking point provided a level of fidelity that modeling alone often lacks. This test exposed structural vulnerabilities that only become apparent under the specific, real-world stresses of hypersonic descent. The upper stage faced equally brutal physical limits. The objective to achieve an intact flight was missed entirely during Flight 8, when the ship suffered a complete structural failure mid-mission. This vector cross-section reveals the root cause of that failure. Inside the payload bay, a composite overwrapped pressure vessel, or COPV, sustained undetectable damage. The tank gave way, causing the propellants to mix and ignite. SpaceX responded with immediate hardware adjustments. For subsequent flights, they lowered the operating pressures of the COPVs, installed protective external covers, and mandated new non-destructive evaluation methods to detect internal microscopic damage before loading propellants. This followed a separate failure on Flight 7, where a propellant leak ignited a fire in the ship's unpressurized aft section known as the attic. To mitigate that risk, engineers installed a new gaseous nitrogen purge system and upgraded the oxidizer filtration hardware. Destroying these vehicles provided the specific telemetry required to identify weak points in the plumbing and pressure systems. These losses served as the data-gathering exercises required to finalize the more robust Block II and V3 vehicle architectures. By August 2025, Those iterative upgrades paid off during the launch of Flight 10. The booster executed a clean ascent burn, successfully simulating an engine-out scenario without losing its trajectory, and placed the upper stage firmly on its planned suborbital path. Once in space, the vehicle completed its first major payload demonstration. The ship successfully opened its payload doors in a vacuum and deployed 8 Starlink mass simulators exactly as designed. This thrust-over-time graph highlights a critical milestone. Engine thrust drops to 0 during coasting, then spikes back up, indicating a successful Raptor relight in space. This capability is required. Without it, the ship cannot execute a deorbit burn or support NASA's lunar missions. Flight 10 verified that the structural reinforcements and plumbing fixes born from previous explosions had successfully transitioned Starship from an experimental test article into a functional payload delivery system. The final physical barrier for the vehicle is atmospheric re-entry. Returning from space means flying directly into hypersonic friction and immense plasma buildup, subjecting the exterior to extreme thermal loads. On early flights, many of the hexagonal ceramic tiles melted or detached entirely, but the telemetry gathered from those damaged sections showed engineers exactly where the thermal stresses peaked, allowing them to upgrade the metallic and ceramic layers until the heat shield held firm. These continuous refinements culminated in July 2026 with Flight 13. The ship achieved its planned trajectory, deployed a payload of functional next-generation Starlink V3 satellites, and successfully maintained its structural integrity straight through the searing heat of re-entry. Guided by its 4 aerodynamic flaps, the ship executed a precise landing flip maneuver just above the water. It completed its descent burn and achieved a soft, fully intact splashdown in the Indian Ocean. The success of Starship wasn't achieved through a linear path of cautious victories. Instead, it was the result of a process that used every failure as a data point to refine and harden the hardware for the next flight.